Go. All right, here we are. I'm going to go ahead and share my screen right away. We have a lot of fun topics to cover. And I'm on the Stardate site. And it looks like one of our observatories in Arizona is threatened by a wildfire. That's not good. Arizona is a wonderful place, as a lot of Southwest areas are. They're deemed, a lot of them are deemed international dark sky sites because they're very dry and they're wonderful places to do observing of the stars. You could really see a lot of the constellations that you can't see as much here when it's lit up in our town. Some places here you can see them very well, like in Cambria, or if you go up to Big Sur, they really come out at you. You could almost not see some of the prominent constellations because it's mixed up with all these other stars that you don't usually see. So where you observe the stars is really important. So anyways, that's up on the news. Early morning hours are really good to see the planets right now. So here's a conjunction is when they're all lined up together. So that's kind of a fun highlight for the summer. And of course, today is the summer solstice. This is the day that we get the most amount of solar radiation. The Earth is tilted most. And I'm going to reduce this here. The Earth is tilted most towards the sun. So as we go through our orbit around the sun, which is also called a revolution, that takes 365.25 days. That's why we have a leap year. But there's our north hemisphere is pointed more at the sun during this part of its journey around the sun. In the wintertime, it's our south pole that's pointed towards the sun. So in 6 months from now, it will be the summertime for those countries in the southern hemisphere. So we'll talk about some of those cycles, and it takes a while, and that's why we have the observation assignment. So if I go to our homepage, I'm just going to highlight you to the assignments that are coming up. If we click on our modules, okay, this is where we're at in module 2, week 2. And there's a lot of stuff packed into chapter 2. So I'm taking a little extra time. There's some chapters that will be quicker and shorter than others. This is one of those chapters that really has a lot of good information that really helps you understand the cycles of the sun, the moon, the stars, and other planets, like how to connect the dots between what we see and what the motions are of some of these celestial bodies and what these celestial bodies are, right? We call meteors shooting stars, but they're really just rocks, debris left over from traveling comets. And we'll talk about that, especially when we get into the solar system dynamics and study more parts of the solar system in the later chapters. Okay, so anyways, do as much as you can on reading. It's really important to kind of go over these terms and topics. And sometimes you have to reinforce it by reading again and doing problems. And there's some suggested textbook problems that align right with our worksheet. And here's our worksheet. So this is a long one, but it has a lot of stuff. And I'll go through the topics. It's like some of the big ones are like, what do we observe in the night sky when we look up? What do we see? Well, we see all kinds of objects. We see stars, we see planets, we see the moon. In the daytime sky, we see the sun, right? And sometimes we see comets and meteors. So we'll talk all about that. And here's your semester observation project. Okay, now it seems really long because I really have a lot of details on it. But this is going to be due about on the last week of class. And there's flexibility because some people might be living in Los Osos where there's cloud cover at night obscuring your views of the sky. So there's a lot of flexibility in what you're able to observe. So just do your best. And the idea is to try to go out every 4 or 5 nights, look at the moon in the moon phase and see how it changes over time. Look at the stars and try to identify at least 2 constellations. And you could even do an asterism in place of it. And then observe those every 4 or 5 days. So you need about 6 observing days for the moon and 4 for the stars. And if you see any planets, write those down as well and try to make note of like how visible those objects are. So it's really detailed. Now, the only other thing that you have to do too is you have to, on a separate time, you have to try to get the sunset or the sunrise and get 2 photos, because over the course of the year, the sun rises up in the sky and then comes back down a little bit. It changes altitude. If you notice in the fall, the sun seems to be lower in the sky than in the summertime. It's really high up in altitude, right? And we have sunsets that are much later in the day. That's because of its journey, its motion, our Earth's journey around the sun and the way it tilts. So there's a change in the sun altitude. And if you were to do this weekly, take a picture of the sun at the same time, at the same place every week, you'll see a big figure 8 in the sky. That's called an analemma. And I will post a link to that as well. I'm going to have a page, but should be your main page that corresponds to your observation project. Okay. There's a lot of really good highlights. So let me just open this up real quick and preview. And then I will fill in some of these details. Okay, so there's a lot of observation tips and notes. You want to pick a spot where there's not blaring lights. Don't go to a car lot where they're selling cars, because those lights are really bright and obscure your views, right? And use your star wheels. You can use a printable or the Edmund Scientific, along with any apps. I use Star Chart. And use the Sky and Telescope interactive page, and we'll show some clips there. And choosing your location is the most important. So what we're going to be observing is we're going to be observing the moon. And for some reason, my sun part is not in here. The moon, the sun, other celestial objects, and you might even see the International Space Station. You can look up on Spot the Station, see when it's visible. You might see that as a highlight. There's a lot of pesky Starlink satellites out there that frustrate a lot of astronomers, because there's thousands of these satellites and they might be taking a long time to try to capture a nice picture of a star cluster or something. All of a sudden there's this satellite that whizzes by right across your photo that they spent hours trying to capture. So there's a lot of those out there. And then we have meteor showers coming up, but it's not really an active meteor time. And those are rock debris that fly through the atmosphere. Sometimes they grow really long tails, and they're associated with the name shooting stars, but they're obviously not stars, because we'd be dead if they were. Another star that close to us would fry us. Okay, so the most important thing is put your when you start your observations, when you end them, and your location. So just pick a times that are convenient for you. And we're going to be tracking the sun here. And I want to try to get either 2 sunrise times spaced, I would try to space them a week apart or 2 weeks apart, and 2 sunset times spaced a week at time. A week or 2 apart. Now, when I say sunset and sunrise times, I really want you to stick to the same time as closely as possible in the same location, because what we're trying to do is see how the sun changes in altitude over the course of weeks. So on the solstice today, we have the latest sunset of the year. So it would probably best to go 20 minutes, take a photo 20 minutes before sunset, and then compare it to a photo another week or 2 apart that's closer to that, that at that same time, because you'll see it go lower in the sky. So that will be really important detail. So I'll be willing to help you as much as possible on that. So I'll definitely have a lot of office hours on Thursdays and other days if you need it. Okay, and then just try to, the other thing is try to have a landmark. It's always good to have a sunset, maybe by a mountain or by the ocean, or have something that highlights where the sun is, or a building. Those are always good. And then just try to sketch it out. And then you can be tracking the moon. You start on a day and you'll notice how the moon's position changes as it goes through the entire month. And try to track what we want with the moon here. Let me back up. Is I think I said 6 observations of it. Yeah, 6. There'll be 6. So, over 4 weeks, you could pick which other extra moon phase you want to do. So just find the appropriate times that work. Look up the rise and set time on the time and date. site that I have in the astronomy resources. That's the best source for looking up sunrise, sunset times, moonrise times, etc. Okay. And then you could even use this calendar, or you could make your own calendar and fill in the phases with the dates, but just put the dates and times in your viewing conditions, and then tracking any planets. If you're up early in the morning, put the planets on down that you see. A lot of times they seem like they're wandering and they have no exceptional pattern to them. We'll talk about that a little bit more as we cover planets. Apparent magnitude is how we relate to brightness of objects in the night sky, how bright they appear to be to us. And when they did the scale, the Greeks didn't have all the objects. So we have like the star Sirius, which is the brightest star in the sky next to the sun, of course. And its apparent magnitude is like negative 1.4. Sometimes some of the planets will get in the negative because they're really bright in the sky. But you could look up those on the Sky and Telescope site. The maximum apparent magnitude is typically listed in Wikipedia for other stars. You can see that the North Star Polaris is really dim. Okay, and then just do like little sketches and notes. This is just like an observational log. And then try to find 2 constellations to keep track of. Do one zodiac, which we'll talk about, and then one other one, and then just observe these over 4 days, span not consecutive days, but like over the course of 4 weeks, and see how the cycle changes, if at all, of those stars. And then any miscellaneous night sky objects, like, did you see a meteor? Did you see a Starlink satellite? Did you see the International Space Station? Did you get to see a comet? Sometimes we're lucky and there's some astronomer somewhere in the world that discovered this like little hazy comet that's coming our way, and all of a sudden we have this beautiful comet in the night sky. I've got to see some exceptional comets over the decades, and they are so fun to watch. They have these huge tails and they really light up the sky if they're good comets, if they're very close and they're really big comets. Other ones, there's what we deem, instead of saying UFO, we call it UAPs, unidentified aerial phenomena. So if you see any of that, you can put that on there. Sometimes there's interesting lightning storms and stuff, and you can write that down. It's a lot of fun to start paying attention to the sky. And a bonus is if you could get like the light pollution app to work. Some students in the past have had problems. There's a Globe at Night. Go to their website and you can look up how you could do citizen science and measuring the light pollution, which is excess artificial lighting that obscures the nighttime objects we view in the sky. Like if we were looking at stars, let's say we want to look at the dog star Sirius, which is the brightest star, and we look at it in LA and it doesn't seem that bright. But if all of a sudden we look at that star in Big Sur where it's really dark at night, we'll see that it's very, very bright. And you could take measurements, you could take pictures of these stars and you could upload them and you could collect some data for them. And if you share that data, I'll give you some bonus points. But it really helps them to identify where the areas of light pollution are in different cities. Because a lot of people in the world of astronomy are trying to reduce artificial lighting and the obscurance of our nighttime view. And then there's a few follow-up questions. I think this is a fun project to do and you could share with your companions. So definitely let me know if you need any help with that. Okay. And as always, I try to keep up to date with the highlights. So just keep on. So with our module here, just kind of giving you a preview. Chapter 2 is a big one. That's gonna be the majority of the quiz on Thursday. And just in this chapter 3 and 4, I have condensed, and it's mostly a lot of reading. And I will put up a PowerPoint there with some stuff, but I have a few. Oh goodness. I have this worksheet here. Sorry, my bird Vega, named after the star Vega, is being very noisy. But it's only like 3 pages here, and it's really highlighting these main contributors of the world of astronomy and what their contributions are. So I'm really just going to draw maybe 5, not more than 10 points from these figures. So from the first 2 pages here. Okay, and then I'll post a little clip, I have some good supplementary videos to watch on that, and we'll talk about some of these other topics here. Actually, I should say pages 1 through 3, because I do want you to know Isaac Newton, and we'll talk about tidal forces as well. Okay, so not very much. I'm going to test you on there, but do your best on that, and I will go over this worksheet. This one will only be worth about 5 points, and we do the beginning of next week. I haven't put it up with a due date yet, but I will. All right. A lot of fun history in astronomy. It's really amazing to see how far we've come. So I've got a lot of supplementary material here as usual, and I will put up my PowerPoint, and I would encourage you to look at these timelines of astronomy and some of these videos as well. Okay, so going back to our cycles and patterns in the sky. I'm trying not to put there's so much good material here. So there's a lot of good things to look at. I will post our Zoom meeting here and in the Zoom recorded links. And here's a lot of really good extra videos. And the text PowerPoints are already put up there. And here's some really good supplementary websites on moon phases, constellations, identifying the North Star, etc. And if there's any others that I see, I'll put on there. But again, I don't want it to be so overwhelming. The main thing is to do your best with the worksheet, with the resources, the astronomy resources page, and what we have here with the PowerPoints and our recordings. So I will post my PowerPoint after today, later on today as well. Okay, so let's see. I will go and start. There's slides here. Yay. All right, observing the night sky. Okay, these are always fun when you see them in Science Museum, these giant star wheels. But anyways, here we are. So our highlights are, we just had a full moon. We got another one coming up. So what you'll see is the moon is slowly disappearing. We call it waning in the sky, where it's not fully illuminated. It's losing its illumination. And then we'll get to a new moon, which is like a non-illuminated moon. It's still there. Okay. And then it'll start waxing, growing in illumination. We'll go through all the phases, and we'll go back to the full moon on July 13th. So as I stated before, if you get up in the early morning, you can watch all of these 5 planets almost align, which is really neat to see. I was looking at what time Sky and Telescope's interactive sky chart will show you where the planets are at the times that you put them in. And then there's a lot of good constellations to look at. I'm going to show you some slides on looking at Ursa Major and Ursa Minor, and how to find the North Star from these. Okay, Ursa Major is the Great Bear, and this is the Little Bear. And I have that discussion assignment on constellations. Some of the other cultures out there, like the Navajos and some of the Asian cultures early, had different patterns. They would identify some of the same stars in these constellations, but they had different names for them. Okay, and different stories behind them, which is really interesting. So one of the big things we want to learn is the difference between constellations and asterisms. Asterisms are groupings that are not constellations. So that's coming up. And we do have 2 meteor showers coming up, the Delta Aquarids and the Perseids. And this is all debris from a comet, but it's coming up later in the summer, but you might see some stray meteors out there. Okay, so I'll also put up some helpful, I know I have a link to how to take photos of the sky with using a smartphone. So I'll put some information on that too, because that could be kind of tricky if you're interested in trying to take your own photos as well. Okay, so when we look up in the night sky, okay, or the day sky, number 1, we see the sun, right? We observe the sun, and we see it rise in the east and set in the west, right? But sometimes it does seem to be higher up in the sky in certain times of year than others. So it's really fun to spot. And when we look more at the details of the sun. We're going to study the sun in detail when we look at the solar system. We'll see that sometimes, it has spots on it that we can't see with the unaided eye, but we can use solar telescopes to view it. It's very fascinating. The sun is a very dynamic, active body that affects a lot of our, can damage our satellites in space, can affect our power grids here on Earth. We'll learn all about that as we come up. We definitely notice the moon and the moon phases. And if you watch closely, you'll see that the moon rises about 50 minutes later every day. So that's something to pay attention to. Sometimes we see these things, planets. They don't look like stars because they don't seem like they're fixed in the sky. They seem to wander. And that's what the early Greeks called them, is wanderers, because, one night they would be in one position in the sky, the next night they've really moved a little bit compared to the other background stars. And most of the stars we see out there seem relatively fixed. They're so far away, we can't see their motion. And different grouping of stars are called constellations. We have an official grouping of 88 of them. We have specific constellations called zodiac constellations. There's 13 of them. And then we have constellations that don't rise or set, which are circumpolar. And then we have other groupings of stars called asterisms. And then the way we map out all these groupings of stars, like the constellations are on a sphere, this globe. If we made a big sphere around the Earth, we call it a celestial sphere. Then we use star wheels and star maps and star charts to help us find these. We also see meteors, comets, artificial satellites, and space stations. So know these terms and distinguish between them. That's the most important part here. Okay, so we see the sun, okay, during the day. We see our moon, the illumination of it, and the moon, what we see on the moon is the reflected sunlight off the surface. So all of a sudden, when you see half of the moon lit, which is called a quarter phase, that really is, that half is reflecting the sunlight, the other half isn't. So it's the way the Earth, moon, and sun are aligned to give you that view of the reflected sunlight. So always keep that in mind when you're looking at the phases of the moon. Okay, so when the Earth orbits through rocky debris, we see meteors. Planets are always sometimes visible. It just depends on Earth's orbit and their orbit. Another word for orbit again is revolution, not to get mixed up with rotation. And then sometimes we see comets, stars. Every once in a while, we'll see a star exploding, which we'll talk about, and satellites. All right. So what you have to be aware of, here we are, the third rock from the sun. Okay. And when we're looking in the sky, here we are positioned in our galaxy, the Milky Way galaxy, which contains about 200 to 300 million stars. That number gets kind of changes and shifts decade after decade, I've seen, as we try to map the surrounding cosmos. But what we see in the night sky is only the stars and the objects of the Milky Way with the unaided eye, right? You need really powerful telescopes to see beyond our galaxy. Okay, so anyways, the thing to keep track of is the motion. Okay, now how do we explain? We see the motion of the sun go east to west, and how do we explain that? What's making it appear to do that? Is it Earth's movement? Is it the sun's movement? Because a long time ago, and this ties into chapter 3 and 4 material, we always said it was a geocentric universe. The Earth was the center of the universe, and the sun and all the other bodies moved around the Earth. Okay, but what we know now is that we're actually moving. The Earth is moving, and we're moving such that it appears that the sun is moving east to west over the course of the day. And the apparent motion of the moon. Now, the moon is orbiting the Earth, but it's really the Earth moon that's orbiting around the sun that's making the motion of the moon that we observe. And the planets, it's the motion of the Earth and the orbits of those planets that are giving that motion that we observe. So these are important things to keep in mind. Okay, so the important thing about the motion of the sun, as we said, eastward relative to the background distant stars is what it seems to be moving. And it's caused by the real orbital motion of the Earth around the sun. Now, through the year, the sun moves eastward among the stars following the ecliptic. The ecliptic is an important term to know, and we'll see this in our star maps. It's the apparent path of the sun that it seems to circle among the stars. So over the course of the year, we'll see the sun in different positions based on our revolution about the sun. And that circular positioning that we see the sun in is called the ecliptic. And I'll show some diagrams because that's a little easier to see. So we know the sun circles, or orbits is a better word, or revolves. We can use all these words interchangeably in 365.25 days. Okay. So we see all this rising and setting based on that. Now, it's important to know that the sun does move, but it seems pretty stationary to us. We have to really look at its motion in the Milky Way. The sun does move and pulls along our entire solar system around the center of our galaxy, the Milky Way, but it takes like 230 million years to do one orbit around the center of our galaxy. So that's really important to keep in mind. Okay, now you're not responsible for knowing this formula right here, but it's interesting how you could do that. Like you could determine your altitude based on how high the sun is in the sky using a certain formula. And the sun altitudes depends on the location where you are. If you're at the equator, its altitude will be different than at 40 degrees. Or if you're further north at 60 degrees latitude, or if you're at the North Pole, okay? There's sometimes the sun doesn't have any altitude, right? We know that the winter months are dark months when you're in some places in Alaska or around the North Pole, okay? So the sun climbs in altitude the first day of spring, up through the first day of summer when it reaches its peak, and then slowly descends again. So it goes to the highest point in the sky and then it slowly comes back down. And in some labs, we've done sun measurements. We've measured the altitude. We would space it out weekly and we could see in the numbers how it changes in altitude. And there's a really good article you could read about that here too. But the main thing to take away here is that it does, this idea that it climbs in altitude first day of spring and then it slowly descends again. Okay, and knowing that pattern. Okay. So the moon does move against the constellations. Now, one thing when you're observing too is we do not like to look at the background stars when it's a full moon because the glares and you can't see anything. So when we have star parties and we have observing nights out there for the stars, we look at it closest to the new moon where there's no illumination of the moon. And we want dark skies, and we don't want any interference with that. Also, when you're observing the moon, maybe through a telescope, we don't like to look at it when it's a full moon. Too much glare. It's too bright. We look at it when it's in its quarter phase. Okay. Now, a really important term is the moon undergoes something called synchronous rotation. And I have some video clips on this. This is important. So the idea is it completes one entire revolutional orbit around the Earth. Okay. So this is like it goes around the Earth in a full month. Okay. That's an orbit or revolution. And at the same time, that's how long it takes to rotate about its axis. So its day and its year are the same length of time, which is 1 month. And I'm using the Earth terms day and year. So think about that. We have a 24-hour day on Earth, and we have a year that it's 365.25 days. Can you imagine if our day and our year were 24 hours both at the same time? That would be synchronous rotation. And it's because of this synchronous rotation, this period that is what we call a synodic month or a lunar month, where we go from full moon to full moon. We go through all our phases. It's because of the synchronous rotation, we only see one face of the moon. We don't see the other side. It's still illuminated. a lot of misconceptions are they call it the dark side and think that there's no illumination. It's still getting sunlight. It's just that it's not facing the earth and we can't see it. Okay. So there's some key ideas. So again, I'm going to highlight this. It changes. The moon rise and set time changes about 50 minutes per day or about 13 degrees. So remember, we talked about a pinky being about 1 degree or a half a degree. So depending on your size of your pinky, you could take if your pinky is 1 full degree, you could take 13 pinkies, and that's how far it changes per day in its rise set times. Okay. And it's really fun exercise to watch the moon. When it does, full moon always rises when the sun sets. Okay. That's a pattern that's always there. So when the full moon is rising during a sunset, one night you could track it every 50 minutes and see how far it's arced across the sky. Okay. And then it'll set when the sun comes up. Okay, so here's a good illumination. So here's some important phases. Okay, so if you start with new moon, is no illumination. Picture number 1 is barely visible. This is a crescent, a very thin crescent moon. So if we had a full moon, which would mean there's not even this little smidget of light here. So I'm going to bring up my highlighter. So this, right, if we erase this little smidget right here, okay, and it's 1 full dark circle, that would be a new moon. Now, all of a sudden, the new moon starts getting a little bit of light, and the sunlight is pointing on this face right here. And the way we are oriented on the earth, we can only see this little silver light, sliver of light, excuse me, and that is a waxing crescent. When it's growing in illumination from slide new moon, which would be 0, to slide 1 to slide 2. This is still a crescent in slide 2. It's a waxing crescent. It's growing in illumination, so that's waxing. And then when we get to slide 3, it's like halfway illuminated. We call that the quarter phase. Okay, quarter, because if it's a ball, it's a sphere, roughly spherical, and we cut it up into 4 pieces. That would be one of the 4th pieces. That's why we call it a quarter. Okay, but to us, it looks like it's half illuminated. And then it's still waxing, it's growing, and then you get to the gibbous phase, okay? And then you get to the full moon phase where it's fully illuminated. And then that slowly descends in illumination. Now it's starting to wane, okay? So it's a waning gibbous, waning quarter, waning crescent, all the way to the new moon. And that cycle takes about 28 days, not exactly. That's why our full moon dates are not exactly 4 weeks apart. So it's really, that's called a lunation as well. It's the synodic month, 1 full cycle. Okay. So it's between the new moon to the quarter phase, that should be about 2 weeks. Sorry, new moon to full moon is about 2 weeks, and back to new moon is 4 weeks approximately. Okay, so really important ideas. And there was something else I was going to say, and here's a way. It's really an interesting exercise to try to think of how you see the moon phases, right? So here's a demonstration you could do. You could have a lamp, okay, and somebody's holding a ball and you're looking at the ball, and the light from the lamp is illuminating that side of the ball, and that's what you see. And if this person walks around with that ball, you're going to see different phases based on your sitting position, your orientation. So this person sitting in the chair right here is the Earth observer. And what we see is based on how it's rotating around us and the light from the sun, which is their lamp. And that's what you keep in mind. So it's really a fun little exercise to do and to be aware of. All right. Now, sometimes, the moon gets an Earth shadow. That doesn't always happen, because what we'll see is that the Earth is tilted and the moon is also tilted about 5 degrees. So it's not a perfectly aligned system. And that's why we don't always get a solar and lunar eclipse every month, which we'll talk about. So here, when you look at an image of the moon right here, we know that the sun is in that direction and illuminating this little silver sliver that we see right here. So one of the interesting thing is when you look at art and paintings and stuff, they always have the sun and the moon phases screwed up. You're like, that's not possible. So if you drew the crescent moon like this, it would be totally wrong and unscientific, but then that might ruin the art perception. So anyways, okay. Now let's think about observing the stars, which is a big one. I'm not going to focus that much on planets because they're tricky, but we're going to look more at the planets with the solar system. Now, we have the sky. This is a celestial sphere, okay, which is a globe of all the star patterns, the constellations specifically that surround the Earth. There's the Earth in the middle, and I have this thing right here that I still have from Cuesta in my room. But if you were to make a big spherical ball around the Earth and you were to divide the sky up into 88 pieces, those are the 88 constellations that are officially designated as constellations, boundaries, kind of like states, you know, they're just like big puzzle pieces that map up to the full 360 degrees of sky. And we use those for navigation or finding other items of interest in the sky. There's 88 of them designated by the International Astronomical Union. Now, this started really from, we adopted the Greek ones. There was 48 official from the Greek that we adopted. And then there's an extra 40 that we added on because the skies that the Greeks saw is not the same skies throughout the entire globe, right? There's a lot of constellations we can't see here at our 40-degree latitude in Slough County because we can't see the same constellations as they can in Australia or other parts of the world. So you have to be aware of this is the entire sky split up into 88 pieces. And so we're going to pay attention to some of the most prominent ones. Now, so we thought of like, you know, when the Greeks made these celestial spheres, they thought of them as fixed points, and we had this fixed sphere of stars surrounding the Earth. But we do know that they move, and we do know that the star patterns shift. So here you can see the zodiac line right here. You see that line? That's the apparent path that the sun seems to follow in its orbit, in Earth's orbit around the sun over entire year. So there's some stars that follow along this ecliptic, and those are the zodiac ones. Okay, so some things about this celestial sphere, and you can make your own globe, and you can get these from a lot of scientific stores. They're really fun to look at. Some important features of the celestial sphere is if we take a line directly from our North Pole and we extend it out to the sky, we have our North Celestial Pole. Okay, so our North Celestial Pole comes right out of our North Geographic Pole, and our South Celestial Pole comes right out of our South Geographic Pole. Okay, and so the horizon is like the limit of where you could see, is the boundary of where land and sky meet. Okay, so like when you're taking a picture of a sunset, let's say on the ocean, the sun is setting just below the horizon as it goes down. Okay, and we call the sunset completed when the last part of the solar disk, the last part of the sun actually goes below the horizon. Okay, so those are important. The zenith is always going to be what's above you. So when you go out in the sky, let's say tonight you want to practice, you go out and you look directly above you. That's called your zenith. Okay, and the meridian is that line. The celestial equator, sorry, let me start with that one. That directly is the, if you extend our equator 0 degrees latitude outward towards the stars, that's our celestial equator. Okay, the meridian is like the halfway point there. And then instead of latitude and longitude, we use right ascension and declination. Okay. So we're not going to get into those details, but a lot of times these telescopes that are computerized now, you write in, if you know the coordinates, every star, everything that we have mapped in the night sky has specific declination and right ascension coordinates. right ascension being like the longitude, declination being latitude. Latitude, declination. Okay, so I just wanted to double check that, make sure I didn't get that mixed up. So that's measured in degrees. So you could type in the coordinates. Like if I wanted to look at the star Vega tonight, I could look up its coordinates. I could put it into a computerized telescope and it'll point it directly at it. So a lot of these modern telescopes use right ascension and declination. And next week, we'll be really talking about lighting telescopes. Okay, which is really neat in the night sky. What you see really depends on your latitude. Okay, again, we're at 40 degrees. So if you get a chance to travel and you could go to the equator or you could go to the North Pole, you'll notice the sky very different. Okay, so the North Star is Polaris right now. That's going to change over the course of time. And this has to do with the orientation. The North Star is something that we could see, and we're at 40 degrees latitude approximately. So this is how we're going to see this right here. We're looking at the Big Dipper, which points to the North Star. So the North Star is not in here. It's just right here at the tip. So it's kind of here's like the Astro. Oh, there it is. Okay, they have it right here. So here's Polaris. Okay, North Star, and that's not really easy to see. You know, it's pretty dim star. So you can see it's about 20 degrees above the horizon. So that means you're at 20 degrees latitude approximately. And if you're at 40 degrees, like here in our county, what you're going to see is here's Polaris about 40 degrees above the horizon. Okay. And then if you go up to 60 degrees, it's going to be about latitude. It's going to be about 60 degrees up in the sky. So if you're at the equator, which is 0 degrees, right? Polaris is going to be right there at the horizon. Okay, you might not even be able to see it's right there where the land meets the sky. But if you're at the North Pole, guess what? Polaris will be directly overhead because you're right at 90 degrees. So if you ever get lost in the world and don't know what latitude you're at, always look for the North Star, and you could try to use your angular measures. Use your pinky measures, your finger measures for degrees, and you could estimate what your latitude is. All right. So the motion of the stars' constellations, some of them appear to have a lot of motion, some don't. So they appear to go westward, and they rise and set in the east and set in the west. Okay, so we'll be looking at rising and setting times. Now, the ones that are very close to the North Star, where we're at, Polaris, they don't seem to be rising or setting. They just kind of circle around the North Star throughout the night. So the amount of stars and the groupings you see really depends on your location, your latitude, and the time of the year. So you have to be very careful with that. So let's take a look at that. Okay, so this is what we talked about, constellations versus asterisms. We have 88 of them, and some of the big ones right now to try to spot, and you can use your star apps as well, Ursa Major, Ursa Minor, Great Bear and Little Bear, which will point you towards Polaris, Pegasus, Lyra, Leo. There's also Aquila the Eagle and Cygnus the Swan, which are all part of the Summer Triangle constellations. And then asterisms are less formal grouping of stars. A lot of, like the Big Dipper is not a constellation, it's actually an asterism. Okay, and the Summer Triangle is a fun one to look for. It's 3 stars that connect 3 different constellations. The Great Square of Pegasus is an asterism. Orion's Belt. Orion is a really prominent constellation. When we get to the fall and winter, it's like what people really identify with and look for. And it has a lot of fascinating objects inside it. And that's why we use these formal regions, 88, because it helps us locate other objects of interest within them. Okay, so let me show you some pictures. So here's an example of the difference between constellations and asterism. Here's the constellation Andromeda. Here's the constellation Pegasus. Okay. And this is called the Great Square Pegasus, which is an asterism. It's a big square in the sky that you can locate. You'll see it on your star wheel as well. Try to see if you could find it. And here we have the intersect. This asterism is in 2 different constellations. Okay, that's the big difference. So here's the asterism, the Great Square of Pegasus, between 2 different constellations. Here is another good example. Here is Ursa Major, all of it. It's a lot of stars. These are really dim. And Ursa Major, again, is the big bear. It's known as the Big Bear. And it has the Big Dipper asterism, which are these 7 stars right here. Okay. And we have the asterism, the Big Dipper, inside this bigger set, which is the constellation. And here's some other notes here. Here we have Ursa Major, Ursa Minor. We have the Little Dipper. This is the Little Dipper. And then here we have the Big Dipper. It looks like it looks more like a scoop cup right here, or a ladle. So anyways, try to see if you can find those. Now here's a fun little trick. These are asterisms again. These are not, this is part of a bigger constellation right here. Now, if you could locate the Big Dipper, you have these 2 stars, Merak and Debi. They point towards the North Star right here. Okay. Now, one of the fun things to do is to see how these circle around over the course of the night around the North Star. All these stars, because the Earth rotates about its axis in 24 hours. What we're going to see is we're going to see these stars circle around Polaris over the course of a night. Okay. So circumpolar constellations, these are ones that are always visible due to our tilt and rotation and our latitude. They never rise or set, and they never fall below the horizon to the viewer. Okay, in the Northern Hemisphere, we have quite a few in here. Okay, they align when you have our North Pole is aligned with the North Star Polaris currently. It's going to change. It'll be pointed towards another star, Gamma Cepheid, in 4,000 years due to the Earth's wobble precession. And in another, I think it's 10 or 13,000 years, it'll be Vega, but it's slowly drifting, and it has to do with the way the Earth is wobbling. I have a little side note on that in an upcoming slide. But what we see is that all these other constellations, these circumpolar ones, go along this counterclockwise direction throughout the night as the Earth rotates. And a lot of people will keep their shutters open on their cameras pointed towards the North Star, and they'll leave it open all night long, and they'll see these star trails that'll form. And that's the stars circling around the North Star. Okay, some of the ones that we have here, circumpolar constellations to pay attention to, are Ursa Major, Ursa Minor, Cassiopeia, Draco, and Cepheus. See if you could see any of those on your star chart apps or your star map. Okay, and that's coming up too, because I'm going to point out how to find those. Zodiac constellations. This is where the big difference between astrology and astronomy really becomes apparent. There's 13 of them, and these are the ones that are along the line, the ecliptic, that path that the sun seems to follow due to the Earth's orbit around the sun. Okay, and anyways, it completes one orbit around the Earth. They all do. There's 13 of them, and we cycle through the entire zodiac. Now, the interesting thing is they're not equally spaced. Okay. Now, astrology, well, like even newspapers still publish these, and they print out like 12 of zodiac constellations for astrology, and based on your birthday. Okay. There's actually 13 of them, and they're not equally the same size. And so there's a 13th one called Ophiuchus, and I'll show you a picture here in the next slide. Okay, so where we are in our ecliptic or in our orbit, the Earth's orbit around the sun, will determine which constellations are visible in the night sky, or in this case, which zodiac constellations. So by astrology, like my birthday is July 12th, I'm a Cancer. And what happens is Cancer is in the sun. So if I go out to look at the night sky, I can't see Cancer. It might be rising and setting around that time, or it'll be below the horizon. So it's really interesting how that works. So in mid-August, Leo is not visible during the night since the sun is in Leo. It's on the sun side, and we can't see it during the day. And but we could see like the constellation Aquarius, which astrology has birthdays associated with it in February. Okay, so here we go. This is what it looks like. Okay, so we cycle through all these constellations, and you can see that some are bigger than others. And here's Ophiuchus, the mystery 13th constellation that astrology decided to omit. I don't know why. But here's the ecliptic. So, you know, we're orbiting around the sun, and we're going to see different parts of the sky based on our positioning around the sun. Okay, here's our nighttime view here. Here's our nighttime view here. Okay, and these are like the true date to the sun when we're in that constellation, when that constellation is right directly in front of the sun. So here's a really nice list you could look at. Okay. Right now we're about Gemini's, just about directly in the sun, entering the sun part. Okay, so here's our star wheel you could get. I'm not sure if anyone's gotten this one or using the printable version, but I'll bring that up. This grommet right here is the North Star Polaris right here. Okay, and what we're going to do is we're going to look at some dates and times here and see how this cycles through. This little oval window is your view of the night sky. Now we're also going to use Sky and Telescope's interactive sky chart, and here's a downloadable star wheel, have an image. So you have to make sure that this is for 40 degrees latitude. Okay, because as we know, if it were made for the equator stars, it would be very different, or if it were made for excuse me, or if it were made for being at the North Pole. Okay, this is what Sky and Telescope looks like when you put in your year, your month, your day, and your different times. And it's really fun to put in hour after hour and see how this night sky changes. Here's some of my apps. We'll have the red screen so it doesn't interfere with your night vision when you're looking at red screen, red light as opposed to white light. You could go back and forth to look in the stars, and it doesn't take you a long time to get your eyes adjusted to the starlight in the night sky. But anyways, this is what you might see in an app. You might see Polaris like this, and sometimes they fill in the whole constellation for you. And you can verify it with your star wheel, how it works on your star wheel. You have your star wheel right next to your app, and you could locate that North Star. Okay, so this is an older one. This is looking at Pegasus. Okay, but this is on January 30th. It's rising on January 30th. So Pegasus, we say it's rising when the first stars appear above the eastern horizon. Okay, and then this is at 7 p.m. We could see Pegasus, the constellation Pegasus. There's the great square right inside there. And then setting on January 30th. That's the last bit of stars right here. Pegasus is huge, but it's the last bit of stars that go below the western horizon. So you might be asked a question like, what time does the constellation Pegasus rise, or what time does the constellation Gemini rise? Approximately. What time does it set? And setting is when the very last stars disappear below the horizon. I'll give you more examples. Okay, this is June 21st. I just added this on this morning. Okay, at 9 p.m. So at 9 p.m. tonight, what you're going to see rising are all these constellations. I can see a little bit of Sagittarius right here. This is a big teapot in the sky. It's a great summer highlight. And there's some special features there. Right around there is the center of our Milky Way. all this little dusty stuff here is our Milky Way. It's the traffic of the stars all condensed together towards the center of our galaxy. This line right here is our ecliptic. So here you're going to find the zodiac constellations over the course of the night going east to west. So what do we have rising? We have, here's a big one, Aquila, the eagle, right here. We have, there's a zodiac. We have Aquila, the eagle, Cygnus, the swan, and Lyra, the heart. This right here forms the summer triangle. Okay. We have these three stars, Vega, Deneb, and Altair, are an asterism connecting these three constellations. So these have just risen. It looks like it's been up for a little bit, but if I go back to maybe 7 p.m., I'd see them right below here. Okay. And then we have also, so there's Sagittarius, which is a zodiac, Ophiuchus, which is a zodiac. We have Scorpius, we have Libra, we have Virgo, and all along here, this zodiac line, you're going to find these zodiac constellations. Okay. Here we have the North Star, and pay attention to how these guys cycle. Here's Ursa Minor and Ursa Major. They're going to go way around there. They're pointing out the Big Dipper right here too, which is part of Ursa Major. So let's see the next slide here, which is your star wheel, the printable one. They don't have it highlighted, but here's Ursa Major, and that should be Polaris right here. And here you can see the setting June 21st. So if you print this out, you'll be able to see it. And here are the same, there's Aquila, Cygnus, and Lyra. Here's the summer triangle right here. These three stars. Okay. Here's some circumpolar constellations all going around the North Star. Cassiopeia, I always like this one. It's a big W in the sky. Cephas, Draco. And then you can see along the zodiac, again, we have Sagittarius, a teapot, Ophiuchus, Libra, Virgo, Leo, Cancer, and Gemini is below the horizon as it should be. Okay, so as you use this paper star wheel, it's a little cumbersome, but that's the link on your page. You could turn it around, you could see how it changes as well. So it completely coincides with the same Edmund Scientific Star Wheel. Now we're going to go to 2 a.m. So we're going to jump from 9 p.m. to 2 a.m. And what we see here rising, notice how this has changed. And here's the summer triangle. There's Deneb, Altair, and Lyra. Here's our three. There's our summer triangle. That's moved a lot. And notice how this has moved. Our Cassiopeia has moved a little bit, but it's just all circling around. The orientations have changed, okay? And this is further along right here. And then summer setting. Where's Sagittarius? There's our teapot. It's moved a lot from where it was over here. Okay, but the important thing is to line it up with the time. So there's June 21st, lined at 2 a.m. Okay, and that's what you're going to see in the sky, and that will point up. So when you could put it overhead and align your east-west coordinates and your north-south coordinates. So I'm going to pause this for a second. And if we do, here's Sky and Telescope, June 21st, if we do 2 a.m., that's what we would see. And it aligns very nicely. So this gives you a really good view. So here you have east going to west. And here's your summer triangle, Deneb, Altair, and Vega right here. Okay, connecting these three constellations. You have your zodiac highlighted in green here. Okay, and also the planets seem to follow these along the zodiac, and that's because they're also orbiting the sun, huh? There's a big connection there. You'll see at 2 a.m. you can see Jupiter and Saturn. There's the teapot. This is a great one to follow. Sagittarius, really good summer one. Scorpius is a little harder to find the grouping. But then we see here's Polaris, and these guys are going to change their orientation. Now look at how this changes if we go to the early morning hours of 5 a.m. Wow. Now we also see Mercury, Venus, and Mars, right? Notice how that changed. See, this shifted, the summer triangle shifted over, and the three constellations, Lyra, Cygnus, and Aquila. Okay. We have some new ones appearing on the horizon here, and we have other ones setting. Sagittarius looks like it's going to start going below the horizon as well. So really important features here to look at. Okay, looks like I'm. And then a little later, we have 6 a.m. changes and so on. This is what it looks like in, this was 2 a.m. today, looking at my star chart app. You can see Polaris, and it helps you identify all the other star locators. You could use that to help supplement. Now, planets are called wanderers because they seem to have interesting patterns. They move a lot more night to night, and that's because they're in close orbit compared to the stars. So there's some that are observing and some that appear to have backward motion if they are on outer orbit, right? Sometimes they'll, depending on Earth's and the other planet's position, it might seem like it'll go backwards and forwards a little bit. So we'll look at that. I'll put some video clips on retrograde motion that are good to visit. Okay, and here's our seasons. So just some more interesting information there. So I added some. So we have 4 main seasons, and it all depends on the tilt during a course of 365 days going around the sun. We're going to be facing the sun in a different position, right? We go through here. There's where we are right here on the northern hemisphere. And then we go through the solstice. Equinox, equal amounts, radiation, equal days, equal nights. Be sure you know that. Now, and then we have our eclipses. We have 2 main types. Solar is during the day, daylight, and it's when the moon can completely cover up the sun. But we do have several types. So the moon, this is a solar eclipse. The moon gets between the sun and the earth and will darken certain spots, but it's a really limited positioning on the earth. Like there's solar eclipses that might be in a small amount of locations on the earth, not visible everywhere. Some people go off to take a cruise somewhere just to view that solar eclipse that we might not be able to see here in California. Okay. And then a lunar eclipse is when we have a complete alignment and the moon gets behind the earth and the earth's shadow is cast upon the moon. We just had one in May, and that's where I was at Joshua Tree taking pictures. We're going to have another one coming up. I think it's October or November. You tend to have 2 that come close to, and it has to do with how the orbits align, the geometry. Okay, so you can look up the dates here. Solar eclipses are very location particular, and the alignment is hard to happen. So because the moon is such a smaller object in front of the earth, the shadow cast on the earth is going to be much different than the shadow of the earth cast on the moon. Okay, so let's see. Here's the main types of solar eclipses to know. What's total is when the moon completely blocks the earth. Annular is, maybe the distance between the earth and moon are a little further away, because sometimes the moon orbit is a little further away than other times. It's a little more distant from the earth than it is at other times of its orbit. That's called perigee and apogee. So what happens is it doesn't completely cover the sun, and you'll have like this little disc. Now, one thing we know is that the moon is slowly moving further away from the earth, a few centimeters every year, and it has to do with the tides. The moon is pulled the tidal torque that the moon is creating on the Earth. The moon is really pulled onto the Earth and slowed its rotation down over time. So the moon has pulled on the Earth and slowed it down. And to conserve angular momentum, the moon has to move further away. So it keeps the spin, the total angular momentum, the exact same value. Okay, so at some point, we're going to have more of these solar donuts, which is the annular eclipse. And the partial eclipse is when it hasn't quite moved into the full path and you're only seeing part of the sun being eclipsed, right? It's moving into the shadow slowly. That's what we mean by partial. So just know those differences. A lot of times, this is very similar to like a transit is when we actually see a planet going across the surface of the sun. Like we'll have a transit of Venus. It's a little different. So eclipsing has to do with completely obscuring or close to complete obscuring of that body, celestial body. And the same with the lunar eclipse, right? We have uneclipsed, prenumbral when we get close to the shadow, total eclipse, partial eclipse when it's moving out of the shadow. So it's fun to pay attention to those terms and definitely know those. So again, meteor showers, visit the meteor shower website. These are, as I said, stray rocks that come through the Earth's atmosphere. And as they move, the friction from the heat creates the light display. The friction from the heat excite the gases in the atmosphere and give off light, which is why we see tails on some of these. And comets that come visiting from the outer regions of the solar system sometimes come flying towards the sun and they get heated up and they degas and they grow this tail from the gases evaporating from the heat from the sun. These are really fun. So I mentioned these before. So one last note I'm going to point out here is when we're comparing things in the night sky, we use something called apparent magnitude, which is different than absolute magnitude. Absolute magnitude is like if we lined up all the stars at the same distance and then compare their brightness, we would have the absolute magnitude scale. But when we look at the night sky and we look at constellations, you have to remember that none of these stars are even closely related at all. They're just groupings. Some might be 600 light years away. The other one might be like 10 light years away. They're completely different groupings, and they will look completely different in different parts of the galaxy. Okay, so there's no association between these constellations other than that they're just a map grouping, and they can be completely different luminosities, different distances, and so on. But when we're just talking about our observations and how bright it appears to be, we use this magnitude scale, this what we call apparent magnitude. And the brightest star is Sirius. Full moon is really bright out there, and the sun is like minus 28 or 27. Okay, and then you can look these numbers up. Like Polaris is really dim. You could look up its apparent magnitude. I think it's like in the 5 or 6 number range. No, actually, it's like lower than that because this is the 5. The Hubble Space Telescope could see really, really dim objects. That's what that's saying there. So here's a few. The symbol we use for absolute magnitude when we take the distance account is capital M sub V. Apparent magnitude is lowercase m sub v. Okay, so when we look at apparent magnitude, which is what's in here, the star Vega is really bright. It's 0.03. That's pretty bright if it's close to 0. The sun, really bright. Let's see, Polaris is 2.02. Antares is a red star. This is a fun one to look for. It's 0.96. So this is how bright it appears to be. And of course, here's our brightest. Now, if we line them up the same distances, that number would change. Something to be aware of. Now, when we look at a constellation, a lot of these have alpha, beta, and gamma stars in them right here. And typically we'll label the alpha stars as The brightest beta stars is the next brightest, and the gamma is the third brightest. So it doesn't always follow along, because as we found more information out, it was kind of like an ad hoc system. But typically, the alpha stars are the brightest in the constellation. Okay, and just to be aware of, there's precession, and this is what we attribute this wobble, slow circular sweep motion. It's like a gyroscope. And I have a gyroscope video. I have a lot of gyroscopes here at home, and I'll go ahead and submit it so that you understand. But it takes like 26,000 years to wobble around. So it wobbles around. And what happens in that process, the Earth's wobble will point, its north pole will point at different stars. Okay. The latest one is Gamma Cephei. And that's going to be the next one. Then eventually it'll be like Vega. It'll be pointing at Vega. I think it's in 13,000 years. I have Centaurus, but I'll put the correct name. It's in Centaurus there. But anyways, it's really interesting how that works. All right, so that was a lot, and there's still more details to be aware of. One of the things to pay attention to when you're out observing is thinking about something called the moon illusion. I'm going to have an assignment for you on that. But anyways, I'll try to add some more video clips, because there's never enough time to go through all that. And I think that's it for now.